Okay, so this week we'll be targeting the topics of pi theorem. I have 3 problems based on pi theorem, kind of solving through these problems as well as explaining its significance, why is pi theorem important. And the last problem will be a Moody flow chart based problem for pipe flow. So let's get started. In this problem, we're told that at low velocities, we can approximate, or I guess determine flow volume, which is Q, volumetric flow rate, through a small bore tube, which is basically a pipe, and Q is a function of tube radius R, fluid viscosity mu, and pressure drop per unit length, dP dx, also known as pressure gradient. And based on pi theorem, we want to non-dimensionalize this term. Essentially, instead of working with 3 different parameters, we want to basically work in this problem, or work with this function as one parameter, just one parameter. Okay. So, what's given was Q, function of tube radius, fluid viscosity, pressure gradient. So, in pi theorem, I guess we get started with this, is we term this variable n. N refers to the amount of variables we're working with. And as you see, we have Q, we have R, we have mu, we have dP dx. Therefore, n is equal to 4, based on number of variables. Step 1 for pi theorem is that we want to write, or get the dimensions for each variable. And so let's start with Q. Q is volumetric flow rate, but based on previous lectures, we usually write Q as V times A, which then returns us units of cubic meters per second, because obviously it's volumetric flow rate. Meters is a unit length, and seconds is a dimension of time essentially. We can rewrite this to be unit length cubed divided by unit time. That's the way we write out variables in terms of its dimensions. We look at what dimensions it consists of and write it down in terms of L, I'll say now, but basically M, L, and T for mass, length, and time respectively. Next up, R for radius. R is lowercase r, it's how it's represented usually, and this is usually in meters. It's at the SI unit, which is unit of length. Viscosity, mu. As an equation, they're really complicated expressions for mu, but the one that we see from class is the Newtonian fluids one, which is that shear stress times the inverse of strain. That'd give you mu, but based on tables, if you were to obtain mu, you went to a table from a textbook and obtain it, you would see that viscosity is written in terms of kilograms per meters second. That's the units it's written in terms of. Which then, if I were to write it in terms of its dimension, kilograms is unit mass, so I write M, meters, unit length, seconds, unit time. Therefore, viscosity is M over LT. Finally, I have dP dx. So what we do next is kind of semantics, but the purpose of what I'm doing is just to break it down in terms of its dimensions. That's why I'm doing what I'm going to do next. So dP dx is kind of like change in pressure over change in distance. Pressure, we think of pressure in its most simplest expression or calculation, which is force per area. And I'm delta x is just x, which is like a length. Force in terms of simplest expression is mass times acceleration, or mass times the time derivative of velocity. I'm gonna move my area down to the bottom. So if I break it up in terms of units, mass is gonna be something in kilograms. Velocity, time derivative of velocity would be meters per second squared. We have unit length times unit area, so meters times meters squared. And I'm working in SI units to keep it simple. So kilograms, that's the unit mass. Moving everything down, I have, I'm gonna have unit length cubed or squared times unit time squared. So that's the expression for dP dx. Meters per length squared time squared. Sorry, mass per length squared times meter squared. So now, I have all 4 of my variables written in terms of their dimension. I said this earlier, but I'll say it again now because it's relevant. We have another term called J. J refers to the amount of dimensions we're working with. In this case, we're working in 3 dimensions. And I'll say it again, unit mass, unit length, unit time. Now, there may be some problems where temperature is involved because temperature is separate from all these three. And if so, J would be equal to 4. But in most problems in this class, J would probably be only equal to 3. Mass length time. Okay. So in step 2, find our pi groups. So how many pi groups do we have? The way to determine the amount of pi groups we have is you take the number of variables, n, minus the amount of dimensions we're working with, 3. Therefore, we're going to have 1 pi group. And the reason we have 1 pi group, which I'll explain right now, is we have 4 terms. We need 3 of these terms to vary across the 3 different dimensions. It's kind of like, if you think of a matrix, we have 3 dimensions we're working with, so kind of like 3 equations or 3 unknowns. 3 unknowns. So therefore, we need 3 equations or 3 pi variables in the pi group to solve for those 3 unknowns. It's kind of like 3 equations, 3 unknowns type deal. Therefore, if 3 of the 4 variables are being used as the pi group, there's only 1 term to non-dimensionalize. Therefore, there's only 1 pi group. And that pi group is equal to, so when we pick terms to be part of a pi group, I should say that, we want to pick terms that are not the main variable, because if I pick q as one of the terms to non-dimensionalize, this function is in terms of q. So I can't even non-dimensionalize the main variable, because then I'll be non-dimensionalizing q with q itself, and that doesn't make any sense. Therefore, I got to pick variables within the function to be part of my pi group, not the main variable that I care about. So our pi group is going to consist of essentially r, mu, dp dx. That's what I'm trying to say. So pi 1 is going to be equal to q times, oh yeah. So q is what we care about, so we're going to leave q by itself. And we have mu, or r, mu, dp dx. And these 3 terms, I'm going to be led to the power of a, to the power of b, to the power of c, because I'll be basically adjusting and varying these parameters in order to non-dimensionalize q. So these 2 terms are going to get varied. Let me write everything in terms of its units. So for q, cubic length per time, r, just length to the power of a, viscosity, m over lt to the power of b, dp dx, m to the over l squared t squared to the power of c. So I have written all my variables in terms of this dimension. I am now going to group my dimensions together. I'm going to group together all the l's, I'm going to group together all the t's, and I'm going to group together all the m's. So L, by default, due to Q, L to the power of 3. For R, L to the power of A. So based on exponential rules, I'm going to add A over. For mu, L is in the denominator to the power of B, therefore minus B. And for my last term, the pressure gradient, L squared is in the denominator to the power of C, so minus 2C. For T, unit time, by default, based on Q, it's on the denominator to the power of -1. T is not in R, so A is not involved, but T is involved in both mu and the pressure gradient, and is both in the denominator to its respective power. Therefore, T would then be minus B for mu, and minus 2C for pressure gradient. Lastly, we have M, unit mass. Unit mass is not involved with Q and R, but it is involved in mu and dp dx once again. Therefore, M is to the power of B plus C. So I've grouped together all my terms, right? For this grouping to be a non-dimensional term, all the L's would cancel out. So L to the power of whatever divided by L to the power of whatever should equal to 1, because all the L's cancel out. All the T's to the power of whatever over T's to the power of whatever should all cancel out to 1. And M to the power of whatever divided by M to the power of whatever should also become 1. So all these terms should be equal to 1, and when multiplied together, they should be equal to 1. So everything should come out as 1, essentially, if we're working with non-dimensional stuff. And to ensure everything equals 1, based on exponential rules, any value to the power of 0 is going to equal 1, right? Therefore, we want all 3 of these terms to have the power of 0, which then gives us the following systems of linear equations. 3 plus a minus b minus 2c equals 0. -1 minus b minus 2c equals 0. B plus c equals 0. I now have 3 terms. what I'm going to do now is solve the system of linear equations, because I have 3 equations, 3 unknowns. So I'm starting my last equation first, and you're all free to solve it how you want to. But for me, I'm going to start here. B is equal to negative c. Look at my second equation. Negative 1 minus b, which is negative c, minus 2c is equal to 0. So I have plus c minus 2c. So I have minus c, and I keep my here. Minus 1 minus c equal to 0. Therefore, c is equal to negative 1. If c is equal to negative 1, this means that b is equal to positive 1. And my last equation, 3 plus a minus b, which is positive 1, minus 2c, which is negative 1, equals 0. 3 minus 1 is 2. So plus a, and this, negative 2 times negative 1, that's plus 2, equals 0. Therefore, a is equal to negative 4. It's just systems of linear equations. I'm just solving some algebra stuff. That's all I'm doing. Therefore, my pi group, pi 1, is equal to q times, I guess, first is r. R is to the power of a, which is negative 4. Therefore, it goes to the denominator. Mu is to the power of b. Therefore, I have b is positive 1, so I have mu on the numerator. Finally, dp dx to the power of c, negative 1. Therefore, dp dx goes on the bottom. And here's my non-dimensional pi group. And the point of this, essentially, you can, I believe, so different setups, different flow setups of this kind of like this thing, will have different q values, different mu values, different r values, different dp dx. And when you plug it in, you're gonna get the corresponding pi value for that flow setup, like that flow through a pipe. So, but despite having like these flow variables, your parameters being different values, if you end up obtaining the same pi group for 2 different types of like flow setups, similar pi groups imply that there is similarity between these 2 setups, essentially. Similar pi value means that, I think in this case, you're basically saying the flow characteristics happens to match between these 2 setups, whether it be flow profile or maybe like flow flow characteristics, flow profile. Something is matching between those 2 cases. Yes.
I just want to make sure, because you said n equals 4 at the beginning of the question, right? By 4 variables, you were alluding to q, r, mu, and dp over dx.
That's correct. Yes. We include the variable of interest as part of that. And you'll see that again in the next problem that I'm going to do if there's no more questions. Okay. So quickly just reading, reading this part. We were looking at pressure drop based on friction flowing through similarly up some long pipe setup. And we see that delta P, change in pressure, is a function of average velocity, flow density, flow viscosity, pipe length, and pipe diameter. So the first 3 units are like flow characteristics. The last 2 are pipe geometry. So, just repeating from earlier, dP is equal to a function of velocity, density, viscosity, pipe length, and pipe diameter. So, as we see here, we have dP, 1, V, 2, mu, 3, rho 3, mu 4, L5, D6. So we have 6 n's. Or just more like terms we're working with, maybe that's a better way of saying it. But let's go through step 1 again. And step 1 was, I believe, breaking down each term into its dimensions. Let's start with dP. dP is force per area. Once again, this is just semantics to get the units, which is mass times acceleration or time derivative of velocity divided by area. In terms of units, I'm going to get kilograms times meters per second squared divided by meters squared. Therefore, delta P is in terms of mass per unit length per unit time squared. Velocity. Velocity is just change, is kind of like rate of change of distance per second or per time, essentially, which is just meters per second, and meters per second is unit length per unit time. Next up, density. Density is mass per volume. In terms of units, it'd be kilograms per cubic meter. And in terms of non-dimensional units, it'd be m per L to the power of 3. Mu. Mu we had from earlier, I'll just write it down again. Mass per unit length per unit time. Finally, lastly is we have first length or axial length of the pipe. Usually I believe it's referred to as x, and it's in terms of meters, which is unit length. Diameter, that's pipe, that's like based on the radial direction of the pipe, so I'm gonna use r as a variable. It's also in terms of meters, which is a unit of time, or length, sorry. It's a unit of length. I've now broken up all 6 of my variables into its dimensions. And once again, I'm working with 3 dimensions: mass, length, and time. Which then brings us to step 2. Step 2 is the amount of pi groups we're working with. N minus j, 6 minus 3, tells us we're expecting 3 different pi groups. This is now more relevant because we have if we have 3 pi groups, it means we have to pick 3 different terms to be part of the pi group, or to like help non-dimensionalize every other term. And this is important because the terms you pick are important. Here's how I go about it. The way I think about it is, I know that by the end of when I do all the math, by the very end, I'm expected to be working with some kind of matrix, right? And the best way to solve the best form to solve a matrix is, I believe, it's called Gauss-Jordan, which is kind of like this form. Does that ring a bell? I want to kind of like set up in this form. And what this form in order to obtain this form, one way you can do it is essentially basically saying, okay, my first term I pick has to include all 3 dimensions, x, y, z. It has everything. So it should have mass, should have time, should have length. The next one I pick should only have 2 of those. It should only have either mass, length, time, mass, time, something along those lines. Should have one of those 2. And the last term should only contain 1 variable, or one dimension: mass, length, time. So for my 3 pi groups, for the first term, I'm picking mu, because mu allows me to traverse in mass, time, and length. The next one I'll pick is density, because density I can then vary, or after viscosity varies, I can then vary in just mass and just length. So basically, like viscosity fixes the time, then I vary between mass and length. And finally, I'm gonna pick D for diameter. Diameter varies in length. So the way I think about it is viscosity varies, and it's gonna lock on for the time. Then rho comes in, density comes in, and it's gonna vary the m until the m is locked in and fixed. Then finally, using D, it's gonna vary the last variable, which is L, and fix the L to non-dimensionalize the term that we're interested in, if that makes sense. But that's what I'm doing. So I picked these 3 terms. Now let's make up my pi groups. Pi 1, the first term I'm going to get rid of is delta p. And I'm going to do so with mu, rho, and diameter, to the power of a, b, and c respectively. Let's break in terms of units. I have unit mass per length times squared. Then I have, for viscosity, m over L t to the power of a. For rho, I have m to the power of L cubed to the power, L cubed to the power of b. And finally for d, it's unit length to the power of c. And I'm going to group these terms first, but as I stated earlier, it should all come out as 1, based on the logic I described from the last problem. Let's group together the m's first. M by default is 1 based on delta p. M is present in the numerator for mu and rho, viscosity and density. So plus A plus B. Look at unit length, by default is -1 based on delta P. For viscosity, it's in the denominator to the power of A, so I minus A. For density, it's in the denominator to the power of 3 to the power of B, so minus 3B. And for C, it's just plus C. Last term is T. By default, -2. And T is only present in viscosity. Once again, as I said, viscosity is going to be fixing the T value. And so, T is in the denominator to the power of A, so minus A. Equal to 0. Sorry, 1, equal to 1. Now, the exponents need to equal to 0 in order for this whole equation to equal to 1. System linear equations, 1 plus A plus B equals 0. Second equation, based on L, -1 minus A minus 3B plus C equals 0. Last equation for t, minus 2 minus a equals 0. I'm going to solve it from the easiest to the hardest. Last equation basically says that a is negative 2. If a is negative 2, the first equation can be written as 1 minus 2 plus b equals 0. Therefore, b is equal to 1. Last equation, negative 1 minus a, which is minus 2, minus 3b, which is 1, plus c equals 0. Negative 1 plus 2, that's positive 1, minus 3, that's negative 2. So we have negative 2 plus c equals 0. Therefore, c is equal to 2. So based on the variables I solved for, here's what my first pi group should look like. I have delta p on the top times mu to the power of a, which is negative 2. So I divide by mu to the power of 2. Next up is rho to the power of b, which is 1, times d to the power of c, which is 2. So when I non-dimensionalize delta p, pressure difference, I get the following pi group as shown here. It's just similar as what we did before. Now, let's work through two more terms. Okay, pi group 2 is velocity. We're working with velocity, and we have mu, rho, and d to the power of a, b, c, respectively. Break it down, L over t times mu, mass over length of time to the power of a, density, mass to the power of length to the power of 3 to the power of b, times length to the power of c, all is equal to 1. I'm going to group together my L term. From v, L to the power of 1. From mu, L is to the power of negative 1 to the power of a, minus a. For rho, L to the power of 3 to the power of b, to the power of 3 in the denominator, to the power of 3, b, minus 3b. And finally, L is to the power of c. For t to the negative 1, t would be in the denominator for viscosity, so minus a. That's it. And for unit mass only exists in viscosity and density. Therefore, be a plus b equals 1. Sorry. All right. Once again, new system of linear equations. For L, it's 1 minus a minus 3b plus c equals 0. For t, negative 1 minus a equals 0. For m, a plus b equals 0. Solving easiest first, which is second equation. A is negative 1. If a is negative 1, third equation says that b is equal to negative a. Therefore, b is equal to positive 1. Last remaining equation, 1 minus a, which is negative 1, minus 3 times b, which is positive 1, plus c equals 0. 1 plus 1 is 2, minus 3 is negative 1. Negative 1 plus 3 is equal to 0. Negative 1 plus c is equal to 0. Therefore, c is equal to positive 1. Let's put together the second pi group. Pi group 2. We have velocity, that's what we're interested in, times mu to the power of a, which is negative 1, so mu is in the denominator, times rho to the power of b, positive 1, times d to the power of c, plus 1. So as a result, we reobtain Reynolds number, which is probably the most known pi group from fluid mechanics. Okay, so that's our second pi group, which is good. Our last pi group, the term we're non-dimensionalizing is L, which is length of the pipe. And I'm going to skip the math because it's kind of tedious. But essentially, it's obviously what's going to return is pipe length is in units in units of length. Obviously, it's going to get non-dimensionalized by pipe diameter, which is also unit length. So it's just unit length over unit length. You're going to get L over D. And the other terms will just be canceled out, P0. So those are your three pi groups. We've non-dimensionalized delta P, change in pressure. We've non-dimensionalized velocity through the pipe, V, and pipe length, L. Those are your three pi groups. So that's part A. Any questions about that? Yes.
How do you know to choose the delta P, V, and L specifically?
It's more like I chose the other three, right? I chose these three, not the other way around. I chose the terms I want to use, remember?
No, like how do you know which ones to non-dimensionalize?
Oh, because I picked these three. I picked mu, rho, and d, correct? So as a result, the three remaining variables would be delta P, V, and L because I didn't pick them.
Would you get the same results if you chose like any other variables? Or?
You might not be able to form a pi group because sometimes you get an impossible matrix to solve, or you get like kind of like you get I think it's like two parallel or two perpendicular. I can't remember what the term is, but equations which cannot be solved. So that could happen. For example, if I did not pick mu and I picked like V instead, or not V, I need a better example. If I pick L, there's no way for me to vary the time dimension. So I would get stuck. I would be like soft locked. So that's why it doesn't matter to a certain extent. But like for example, if I change rho with V, I think I can get away with it. Like it should be okay. Yeah, any other questions? If not, just quickly speaking, because I have the solution. Part B, you're given this table of different values. Essentially, what they want you to do is they want you to solve for pi 1, pi 2, and pi 3, and basically form 3 new columns based on this information. And based on those 3 columns, you then plot this following plot here, shown by the circles, the non-filled circles. And so, as you see, we have pi 1, which is your delta p, essentially some non-dimensional form of delta p. And delta p is being determined by obviously first, but pi group 2, which is your flow characteristics. So flow characteristics is being varied. And we also have pi group 3, which is the pipe geometry, and pipe geometry is being varied. And what you'll see is that delta p, which is, remember, what we basically did was pi 1 is now a function of pi 2 and pi 3. That's essentially what we did in this problem. And when we do so, we're going to get the following function lines, or the following results, which is these plots. And if we were to match our pi 3 terms, you'll see a family of functions that follow this trend. And what part C basically is asking you to find, or basically realize, is that based on what we've plotted down, we see that there is a linear relationship between pi group 1 and pi group 3. So if we were to fix, if we were to fix pi group 2, there should be a linear relationship between pi group 1 and pi group 3. And that trend's meant to be shown or made apparent via plotting this stuff down. And that's one of the reasons why the pi groups are like very useful in engineering. When you non-dimensionalize stuff down, it's easier to visualize trends. Any questions about that? Okay. If not, let's go to the next problem. I'll go over this quickly. We have 2 more problems, but essentially we have this Venturometer set up, and basically we put in some fluid, and we run the fluid at a certain speed through this tunnel, essentially. And as a result, the manometer here will basically show what the pressure difference is based on the fluid you picked and its velocity. You guys can have pressure difference, essentially. And so we have two different runs. This first run, we're using water. And in the water run, we know that the density of water is, I think it's like, at 20 C, it was like 980 kilograms per cubic meter. And we have the speed of the water, 4 meters per second, going through this tunnel. And then we're also given the pressure drop, which is based on, which is based on the manometer. The manometer gives the delta P, once you solve for it. But delta P is shown to be a 5 kilopascal pressure drop based on this fluid flow. And then basically after doing run 1, these researchers want to do run number 2, where we change the fluid to be gasoline. And in the gasoline run, I think we're given, I have the density, but we're given a density, and we're given that the pressure, we want the pressure gauge to be, the pressure difference to be 115 kilopascals. I think the gasoline one was 680, but let me recheck in a bit. All right, and we also associate some V. but this velocity is unknown. First up, we want to be able to match the flow characteristics between both cases in order to obtain this v value, because we want to make sure that the velocity is comparable to the other case, essentially. So to make this comparison, essentially, there will be some kind of non-dimensional analysis that occurs, and the resulting non-dimensional term / pi group, you'll obtain pi is equal to delta p, pressure difference, divided by rho v squared. So what you have here, this is a form of static pressure. And down here, this is dynamic pressure. So if you remember back to the Bernoulli's equation, or maybe it was the Bernoulli's equation, that's like static pressure is the internal energy term, and dynamic pressure is kind of like the kinematic viscosity term. Kinematic energy term. And essentially, combining static and dynamic pressure together, you will basically re-obtain total pressure for your system. So those two terms are the same dimensions. They're both in terms of pascals, and they would non-dimensionalize each other. So that's our pi group. So let's first solve for the pi group for run 1. For run 1, we have a pressure difference of 5,000 divided by rho of 980 kilograms per cubic meter times velocity of 4 meters per second squared. As a result, you will get pi value of 0.3189. Let me just double check quickly what exactly was the density of gasoline. I don't remember. Nope. Okay, it was 680, but I got the water one wrong, which is fine. This is a math error. Okay, but now, given that pi 1 is equal to this value, let's plug in these values. Pressure difference of 15,000 pascals divided by density of 680 kilograms per cubic meter times v squared equal to equal to pi group 1. Therefore, v squared, or v, is equal to square root 15k pascals divided by 680 kilograms per cubic meter times pi 1, which is 0.3189. Therefore, v is equal to 8.32 meters per second. So that's the velocity we want in our gasoline case in order to have the flows match to that in the water case. And finally, while we match the flow, we still need to match the geometry. That's another important thing. I don't know if it was discussed, but in order to obtain, I think it was dynamic similarity, you need to have geometry similarity and also kinematic similarity. It's like a law or a rule. And with those two matching, you basically have the same flow field in both in run 1 and in run 2, which is our goal. So to match, I guess I'll match geometry. Q is equal to VA. And I think we're trying to solve for A. So we have Q for the gasoline case. Q for gasoline is 3 cubic meters per minute, which is 9/60 cubic meters per second, is equal to 8.32 meters per second times A, which is pi over 4 times D for the gasoline case squared. D is equal to square root 960 cubic meters per second divided by 8.32 meters per second times 4 pi over 4. And the result, you'll get D is equal to 0.1515 meters. So that should be the entrance diameter for your tunnel for the gasoline case. So we need to rescale that dimensiometer in order to get geometric similarity. Any guess?
Was 9/60 given?
So we're given 9 cubic meters per minute, and I scaled it back to seconds. All right, any questions about matching, I guess, geometry and kinematic similarity? All right, if not, last problem. This problem is based on the Moody flow chart. So let's read this problem statement and also write down our givens as we go along. Oil, so this case about oil, with a viscosity, a density, 450 kilograms per cubic meters, and a dynamic viscosity, which is viscosity divided by density, of 2 times 10 to the power of negative 5 meters squared per second, which, by the way, so these are flow characteristics. It's flowing through a 30 centimeter pipe or 0.3 meter pipe with a pipe, and the pipe has a length of 100 meters. So this is pipe geometry. And we're given that as we're going through the flow, we have a head loss, which is like the, due to friction, of 8 meters, and we're given a roughness ratio of 0.0002, and these two terms I would refer to as pipe. That's the pipe characteristics. Maybe not. Maybe this term is a little different, but that term is pipe characteristic. And we're interested in finding average velocity, which also can give us the volumetric flow. Yeah. So we have these, as you see, I've been labeling our givens, and the reason I'm labeling our givens is that based on flow characteristics and based on pipe characteristics, essentially, these two terms, in a way, these are kind of pi groups. Like flow characteristics forms a pi group, pipe characteristics forms another pi group. How is the surface of the interior of the pipe? What's its roughness value like? What's like the finishing like? That is pipe characteristics. Flow characteristics, how fast is the flow, what's its viscosity, etc. So those two parameters or those two terms plays an important role in determining their interaction is going to generate a certain friction factor, which is known as the Darcy friction factor. So this friction term, this friction variable, is a function of flow characteristics and pipe characteristics. F, which is, as I said earlier, the friction factor, Darcy friction factor, is equal to head loss multiplied by pipe diameter divided by pipe length times it's the inverse of velocity head, so 2g's over v squared. That's the function for F. I'm going to plug in my known, so I have 8 meters for head loss. Pipe diameter is 0.3 meters divided by pipe length, 100 meters, times 2g's, which is 2 times 9.8, divided by v squared. V is unknown. V is what we're interested in solving for. So F is equal to F is equal to 0.4704 divided by v squared, which then implies that, by this relationship, it implies that v is square root of 0.4704 divided by f. So we have a way to correlate between v and f, but exactly how can we determine f? This is what brings us to the Moody flow chart. All right. So in the Moody flow chart, here's what we got. Here's what is important to discuss. Essentially, if you look at the right-hand side, relative roughness, that refers to your pipe characteristics. That's how rough the interior of the pipe is, because how rough it is plays a role in that friction factor. Like if the more rough the surface is, which is correlated by how the higher the value. So higher values means a more rough surface or rough finish inside the pipe. It refers to a higher friction factor. Lower values refers to less friction, or lower friction occurrence. So that's that right-hand column. The x-axis, your Reynolds number, that is the flow characteristics I'm talking about. How fast is the flow? How viscous is the flow? Is it gonna, because high viscosity lower Reynolds number, which refers to either a slower flow or higher viscosity, that refers to obviously more friction, because obviously at these lower values, you see at these lower values you have higher values of F, or you have higher values. and at higher value of Reynolds number, which means faster flow and lower viscosities, we obtain lower values of F. And F is left-hand side. I should have said that first, actually. F is the friction factor, how much friction would occur over a section of a pipe. So once again, lower pipe roughness values means lower friction. Faster flows or low viscosity flows would result in lower friction factors or friction occurrence. So as you see, these two roles, your pipe characteristics and your flow characteristics, those two play a role in determining what the friction factor is. Did I make that clear over this chart? Yeah, friction is, once again, one last time, friction is dependent on these two terms, Reynolds number and relative roughness. That's what I mean to say. In this problem, we don't know what the velocity is. That's what we're trying to solve for. We want to know what the flow in the pipe is, and without knowing what the speed is, we don't know what the Reynolds number is. So we cannot fix the x-axis. X-axis is we can't fix that. What we are given though is the pipe roughness. That's what we're given. That's the right-hand side. That's like a family function or like, yeah, we're given relative roughness. Our relative roughness is this one. We're given that relative roughness is 0.002. So therefore, what we do know is that no matter, like, as we're solving this equation, we should be along this line. I wish I was better at drawing, but whatever value we get, we should fall on that black line there, no matter what. And as I said earlier, with a fixed roughness, so roughness is fixed, lower Reynolds number or slow flow or high viscosity flows, that's gonna result in higher friction factors. However, fast flows or low viscosity flows, that's gonna result in lower friction factor values. And in the best, and as you see, eventually, no matter after a certain point in the Reynolds number, no matter how much more you increase the Reynolds number, the friction factor is gonna start to plateau, which implies that there is kind of like a best case scenario for friction. You can't get a friction of 0. There's only a best case scenario where the lowest friction occurs. In our case of 0.002 for the relative roughness, we see that best case scenario is that the friction factor is 0.014 essentially. That is the best case scenario. You can't get better than that. So what we're going to do to solve this problem is we're going to assume best case scenario. Which means you minimize the F value. So for friction relative roughness factor of this value, best case scenario is equal to 0.014. That's the lowest friction factor you can get for this roughness type, or for this general roughness. And so we're not going to iterate. What I mean by iterating is essentially we're going to guess a value for F. So we're going to guess the best case scenario here. And we're going to travel up and down this black line until eventually we settle onto a point. And that point is going to be our final answer. So let's do that. Iteration 1, F is equal to best case scenario. If F is equal to best case scenario, velocity is equal to the following. That means velocity is equal to 5.797 meters per second. So for the best friction case, we expect this velocity. Finally, now we have a velocity, we'd actually determine a Reynolds number, because as I said earlier, we didn't know a Reynolds number, we just assumed best case scenario. But now with velocity, we can obtain a Reynolds number. Actually, and I'm labeling 1 for first iteration. And sorry, Reynolds number is rho v d over mu, which is also v d over nu. I have obtained the following calculation. So that's my Reynolds number. I plugged in everything. I get Reynolds number of 86,950. That's my Reynolds number. Okay? So let me return to that plot. What the heck? Oops. So Reynolds number is 86, basically 87,000. And 87,000 would be around this value here. So based on the Reynolds number, I move up and I continue to follow my 0.002 roughness factor, right? Therefore, I have a new interception. This new interception is going to give me a new F value. Or did I mess this up? Yeah, sorry, 1 second. 87,000 is over here. Which gives me a friction value somewhere around here. So one way you can solve this problem is just looking at this chart. Another way you can solve for it is using this equation here. This is an interpolation formula. However, it's very hard to calculate using this. So I think best case scenario is either have you graph it on a graph calculator to determine where the what F values would work, or use this table. Those are the two ways to go through this problem. I did this using I think MATLAB, but if you use that calculate using this formula, you obtain that based on this Reynolds number, you get that your new friction factor based on this Reynolds number is 0.02011. So we assume best case scenario, which is 0.014, but as a result, our resulting velocity characteristics do not match up, our following velocity characteristics that we obtain from this friction factor do not match up, because based on these values, we get a new friction factor that is 0.02011, which is a higher friction factor. And obviously, as you see, we move up the plot, or we move leftwards of the plot, and we move up in terms of friction factor. So our initial guess was wrong, but we have a new guess, which should be closer to our answer. And let's check that. And the way we check that is we iterate again. So iterate again. Based on this friction factor, what is the associated velocity based on our equation? So you get 5.7, square root of 0.4704 divided by 0.02011. So my new velocity is 4.836 meters per second. So our velocity changed. That's fair. And our Reynolds number is going to change too then. So 4.836 meters per second times 0.3 meters divided by 2 times 10 to the power of -5 meters squared per second. So my new Reynolds number is 72,550. So if I were to plot this, new Reynolds number would be about, I think, here, maybe. You get a new friction factor. And essentially, as you see, now the new friction factor is much, the difference between the gaps is much smaller. And essentially you keep iterating until you get to a value which if the value does not change enough, you basically say that, okay, so even if I keep doing this process, not much is gonna change, right? So in this case, I believe actually when you do the calculations, you should obtain a friction factor, the next friction factor should be the same as the one before. So you should reobtain the same friction factor actually, technically. And because these two values match, even if we iterate again, we're gonna get the exact same values again. So there's no point iterating anymore. Therefore, based on this value, or based on the fact that our iteration is not yielding new F values, this is our final velocity for our problem. Any questions on that process? For me, the main takeaway is the fact that friction factor is a function of flow characteristics and pipe characteristics. However, there's no real way to associate the two, besides this weird interpolation formula. Therefore, this Moody chart is able to showcase trends and characteristics and way to interpret these values. And that's why the moving flowchart is important, pi groups are important, and yeah, that's my discussion. If there's no question, thank you and have a nice day.